Today we are going to solve an example problem on deflection of beam under bidirectional bending. So the problem that I have chosen for today's lecture is a simply supported beam but with an overhang. So you have solved this kind of problem to find out the bending moment and shear force diagram in your first year mechanics as well as later. So this beam, which is simply supported at the 2 points B and D, has an overhang of length L. Okay, a load W is acting at the free end A. The problem that the cross section of the beam is shown in the figure. Okay, so this is the cross section of the beam at XX at C. The section XX is actually at the point C. So the question asks us to find out the deflection U and V, U being the deflection in the Z direction and U being the deflection along X direction and V is the deflection along the Y direction. So this is X direction and V is the deflection in Y direction. Okay, so let us try to solve this problem. So as you may be able to appreciate that the first step that we need to do to go ahead with solving this problem is to find out the bending moment at C, or the moments mx and my at C. So let us do that. So if I just try to redraw the beam, so let me consider that the reaction at the two simple support B and D are R1 and R2, and W is the load applied at the free end. So this is D, this is B, and this is A. Now if so R1 plus R2 is equal to W. That is my first equation. And if I take moment about B, then I have R1 into 2L plus W into L is equal to 0. So that implies R1 is equal to minus W by 2. So this is my equation 2. So see, I wouldn't go ahead and solve the entire problem, because what I need is just the moment at position C, which is midpoint between B and D. So I just need to find mx and my at B. So bending moment at C is therefore R1 into L, which is W2 into L, and that is mx. So mx at C is WL by 2 and my is equal to 0. Now let us look into the sign of the mx. So sign of mx is going to be positive. Okay, so because if you try to visualize, the moment at C is going to be in the in the clockwise direction. So this moment you have to visualize it here. I probably wouldn't be able to explain it by drawing a figure. So you have to kind of visualize this, that the moment at C is only because of R1, so which is going to be WL by 2. Now WL by 2 is going to produce a tensile stress in the first quadrant of the cross section. Okay, therefore this moment is a positive moment. So WL by 2 is a positive sign moment. Okay, because according to our sign convention, this mx at C is going to be producing tension in the first quadrant of the cross section. Okay, so now my first job is done. So I know that mx is equal to wl by 2 and my is equal to 0. So let me just erase this part and go ahead with the rest part of the problem. Okay, so I say that mx is equal to wl by 2 and my is equal to 0. So as you may try to understand, so this is the first step done. Okay, let me even call this a step. Okay, the second step it would be to find out the sectional property. Okay, so the second step is going to find out the sectional property. Okay, so first let me find out Ixx. As you will be able to appreciate that the centroid of the cross section, because of the symmetry and antisymmetry, is going to pass through the midpoint as shown. So this is the centroid of the cross section. Okay, and x and y are the centroidal axis. So let me try to find out Ixx. So Ixx is going to be, so I'm going to consider of this part. So I'm first going to find out Ixx of this part. Okay, so Ixx of that part is going to be 1 by 12 2a whole cube into t. Okay, right? So now the next job is going to be to find out the Ixx of this part and the Ixx of this part. Okay, now if you remember what I said for the thin wall cross section is that the Ixx about its own line, this one, will not be considered. Okay, because this is not going to be considered. Okay, because it is going to involve a term with t cube which is too small and can be easily ignored. Okay, so I will not consider the Ixx of that part. So I am left with only therefore 2 times for the top and bottom part, AT being the area of the top and bottom part into a square. Okay, so that is going to be only the value of the contribution from the top and bottom horizontal part. Now let us move into this two part. Okay, so for this two I have 1 2 into, for both bottom and top part, 2 into a by 2 whole cube into t plus 2 into area, that is a by 2 into t, plus the distance from the central axis, which is a minus, which is going to be a minus a by 4 whole square. Okay, so if I calculate this, this is going to be 8. So 2 by 3 a cube t plus 2 a cube t plus 2 4 1 by 48 a cube t plus 9 a cube t by 60, if I have done it correctly. So if I sum this two up, I have this as 13 a cube t by 4. This is going to be 13 a cube t by 4. Right, so my ix is done. So let me now find out iyy. So iyy of the middle uh, portion is going about its own axis is going to be 0. So about its own axis, this axis is going to be 0. This we are not going to consider because it will involve a t cube part. So that part need not be considered. So therefore, if I write iyy, so it is going to be only the top and bottom portion, which is going to be 2 into 1 by 12 a cube t plus 2 into a t into a by 2 whole square plus again about this a by 2 portion, the iyy about its own axis is going to be 0, is going to be neglected. So I just am going to have 2 into a by 2 t plus into a square. Right, that is what I'm going to have. So I have a cube by t by 6 plus a cube t by 2 plus a cube t. I hope I have done it correctly. So I have this as, if I add this 3 up, I am going to get this as 5 a cube t by 3. Okay, so our next job is going to find ixy. So let me just erase this all off. So let me just write down that ixx is 13 a cube t by 4 and iyy is 5 a cube t by 3. Okay, so now let me find out ixy. So ixy for the middle portion is going to be 0 because it's passing through the centroidal axis. So I have to take ixy of the top and bottom portion. So let me take the top horizontal portion. So that is going to be at. X is going to be minus a by 2, y is going to be a. And if I take the bottom portion, it is a by 2, x is going to be a by 2 and y is going to be minus a. If I take the two small vertical portion, this is going to be a by 2 t, x is going to be minus a, y is going to be a minus a by 4. Okay, and then plus a by 2 t, I have positive a and I have negative of minus a plus a by 4. So that is going to be 2 times, So that is going to be 2 times a cube, sorry, this is going to be a cube t plus 3a cube. So this is minus a cube t, and this is going to be minus 3a cube t by 4. So this is going to be minus 7a cube t by 4. Okay, so that is the value of ixy. So let me write down ixy is going to be minus 7a cube t by 4. So done. So this part is then done. Okay, so I have got the sectional property. Now let me go back to the expression first. So the third point would be to go back to the expression of d2u by dz square and d2v by dz square is going to be minus okay. So in this equation my is equal to 0. Since my my is equal to 0, so this equation can actually be simplified and written as del 2u del z square is equal to mx ixy by e ixx iyy minus ixy square, and d2v by dz square is going to be minus mx into iyy okay. So this are going to is going to give us the expression relating the displacement with the moment and the sectional property. Okay, now I can actually clear the canvas and use the value of ixxy and iyy here and try to find out u and v. So if I do this, my d2u by dz square is which can also be written as u double dash is going to be, if I plug in all the values, you will see if I have done it correctly, it is 0.372 into WL by E into A cube T. So if this is the value of u double dash, let me see what is going to be del u by del z. So del u by del z is going to be minus 0.372 WL z by E A cube T plus C1. Okay, that in turn is going to be giving me u, which is going to be a function of z, is minus 0.372 WL z square by 2 E A cube T plus C1Z plus C2. Okay, now I have to apply the boundary conditions here. So the boundary conditions says that U Z at at D, where Z is equal to 0, is equal to 0 because it is simply supported. Okay, so that is going to give my C2 to be equal to 0. Okay, now the other boundary condition is that UZ at B, where Z is equal to 2L, is also equal to 0. Okay, so that is going to give me the value of C1. So if I plug this into this expression, I will get C1 as point. So if I plug this in, then C1 is going to be 0.372 WL square by E A cube T. Okay, so therefore if I finally write it down, UZ is going to be equal to minus 0.186 WLZ by E A cube T plus 0.372 this is Z square, this is Z E A cube T. So this is the expression for UZ. Okay, now in order to find out U at C, I have to put Z is equal to L. So that is going to, if I put Z equals to L, I am going to, and I solve it, I am going to get this as 0.186 W L cube by E A cube T. So that is going to be the value of U at C, which is at Z equal to L. So similarly, I can solve for V, and you will see that if I solve for V, so similarly, I'm not repeating the entire calculation. So similarly, we can say that V at C, which is Z equal to L, if you find it out, it is going to be minus 0.177 WL cube by E A cube T. So this is the second part of the answer. Okay, so with this I am done with the problem. So we have solved the problem, we have found out the values of the deflection as a function of Z, which is the lengthwise axis of the beam, as well as we have found out the deflection at the asked point, that is C. Now with this example we end the topic or module on bidirectional bending of beam. Okay, let me summarize what are the essential points to be remembered about the bidirectional beam. So for bidirectional beam, the neutral axis is going to pass through the centroid. The neutral axis is going to make a certain angle with x and y axis, and that angle alpha will depend not only on the sectional property but also on the applied moment mx and my. Now the third point is that all this derivation has been done using Euler-Bernoulli beam theory, which assumes that the plane sections remain plane even after bending, and it remains perpendicular to the neutral axis even after bending. So the fourth thing that we did is to find out the deflection of the beam at a given point on the lengthwise axis, and we see that we can find out if we know mx, my and the material property and the sectional property, and of course also the material property, because we are using the Young's modulus E. Now if you try to understand, so you have seen, particularly in this example, that even if there is no my, it is almost an unidirectional bending, right? We have only mx, okay, but even then you are getting both the deflection u and v, which is unlikely, which you have not encountered earlier. So earlier you had mx and only you had u. So here we are getting both u and v, in spite that there is only one moment mx, because of the unsymmetricness of the cross section, because the ixy value is not equal to 0, and that's why you are getting a deflection in both u and v direction. Okay. And the last point that I want to say about it would be a little bit difficult to probably explain without by writing or drawing figures, is that, see, when we have bidirectional beam of any arbitrary non-symmetric cross section, okay, you can imagine it to be an unidirectional bending about the neutral axis. So when as soon as it becomes a bidirectional bending, or there is an unsymmetry in the cross section, the neutral axis is at a certain angle with the x-axis. Okay, and you can actually think of it as an unidirectional bending about that neutral axis, about that inclined neutral axis. If you can visualize this, I'm not sure whether you will be able to visualize, because I'm not being able to explain it physically. So if you can probably visualize this, then you will realize that even bidirectional bending or unsymmetric cross section, bending of unsymmetric cross section, is a kind of, can be transformed, can be imagined or visualized as unidirectional bending about the inclined neutral axis. Okay, so with this I am going to end this lecture. Thank you.